So like I was saying, I was talking about Lagrange multipliers yesterday. Um, and we were here in section 3.4. Fixed a typo earlier. This said 3.5 on the title slide, but I fixed it. It should be 3.4, like it says on screen right now. I think we'll be able to get through this section and maybe even start chapter 4 today, which means we're running a little bit ahead, which is good sign. For now, we're going to jump back in here. We did one example yesterday of Lagrange multipliers, which Lagrange multipliers are the method of Lagrange multipliers is basically just setting up this equation right here. You take, you're trying to find the extrema of a certain function, f. You're given some constraint, g, and you're the level set of that constraint. If that function has an extrema, then, or an extremum, then it satisfies this equation with this extra Lagrange multiplier here. That's this lambda thing. And we're going to see a few different examples here today. We saw one yesterday. Let's jump into that one. So we saw that it does take a bit of work, this method of Lagrange multipliers. In fact, it took us a slide and a half. Normally we could fit all our work on one slide, but this one takes a little bit more, but none of it was particularly difficult. I think the hardest parts, like, at first you take a couple of gradients, and then you set up this system of equations, which my work is kind of messy here, but yeah, if you were here yesterday, you remember we set up the system of equations right here, and that gave us kind of the setup for solving for x and y. And along the way, you usually solve for lambda, as we saw. You saw that over here, the bottom right. You saw that you solve for lambda. That's not always going to be the case. Sometimes you're going to be able to just use lambda as a placeholder and just directly solve for x and y, or x, y, and z. But in this case, we solved for lambda, and then we're able to use that to solve for x and y. And in this case, that actually gave us two candidates for extrema. Remember, the method of Lagrange multipliers just finds you candidates for extrema. It doesn't actually determine whether they're a minimum or a maximum. It's just for finding candidates for extrema. And in this case, we then just, in all the cases, all we're going to do is just plug those values into the function, see which one's biggest, see which one's smallest. That's going to be minima and maxima. That's the strategy here. Okay, and we're going to outline that strategy a little more. But what I wanted to do today is explain a little bit more with this problem in particular, what is going on in the picture. Can I draw a picture of what's going on with this, kind of explaining more conceptually why the method of Lagrange multipliers works, right? So first of all, let's talk about this function here. Let me give myself a new page. So we have f of x equals x plus 2y. Oops. X plus 2y. And then we have our constraint function, which was x minus 2 squared plus y minus 2 squared equals 1. So geometrically, this here is a circle. So let's draw this picture here. This is the circle centered at 2, 2, right? So we have this, we have this, and we have a circle centered at 2, 2. Okay, so that's this right here. Radius 1, so maybe I'll try to be a little more to scale. So something like this, right? 1, 2, 1, 2, something like this. This is something like the constraint that we're restricting this function to this. But if we just look at this function here, what shape will the graph of this function be, right? So if I say f of x is equal to x plus 2y, or in other words, z is equal to x plus 2y, what shape will that graph be in? What geometric shape, what kind of shape in 3D space will that be? Okay, we haven't learned the names of a lot of them, so my hint is that this is something that this is a shape that you know. It's nothing crazy. What shape would the graph of this be? So a couple of ways to approach, if you're not sure how to do that, you can look at the level sets, right? The level sets of this guy would just be lines, right? Because you just have 0 equals x plus 2y, 1 equals x plus 2y. You can always just isolate the y and get some kind of y equals mx plus b thing. So if you have a function such that all of the level sets are just lines, and those lines are basically they're all going to be parallel, it's just going to be them moving like across the screen, across the plane. Okay, so what is, if the level sets are all lines, what does the graph of this look like? Okay. Any takers? The graph of this guy, right? So you have your x and your y and your z. It's going to be, and I'm going to do my best to draw it, but you can also type it into GeoGebra. You get a plane, and I'm not going to draw the angle very well, but it's going to be something like this. Okay, so plane, something like this. This one happens to go through the origin, happens to hit this point here, but you get something like this. Okay. And geometrically, now let's think about geometrically, what does the gradient represent for this function? What does the gradient of a function represent? It's a direction, right? Because you get a vector out, right? So what does the direction geometrically represent? Takers, go back through your notes, right? So I think I formally wrote that one down in section 2.6. I wrote down formally that the gradient represents the direction of greatest increase. Remember that? So if you're standing somewhere on the graph and you want to increase and you want the value to increase, then you take the gradient and plug in that point wherever you're standing in the graph. Okay. It's an important note. It may have, I think it's an important note. You should know how, you should remember this sort of intuition for what the gradient is doing. You should know this, right? Okay. In the case of a plane, the plane is just growing in one direction, right? You can, which is why in this case, remember back to this, the gradient of f was just a constant 1, 2. 1, 2. Because the gradient is growing just in one direction. And then in fact, it comes from these coefficients here. So it's just growing in this one direction. So what I'm going to do is I'm going to plot the gradient of f over here. Okay. So what we actually get is something like this. But remember, it happens at every point. At the gradient you can think of as, we're going to learn a little bit about next week something called vector fields. So at every the vector the gradient is happening at every point. Now at every point it might be different, right? But in this case, at every point it's the same. So it's just this sort of vector field, or it's just this collection of vectors that's based everywhere, something like this. Oops. Something like that, right? Okay. So everywhere you get this vector in that direction. You just have vectors everywhere pointing in that direction. Okay. Now let's pause for a second and remember, what does the gradient of G represent? Again, this is, if this is G over here, I should use a different color. The gradient of G, where again, G is this thing over here. This is G. The gradient of a constraining function, now it's also the gradient, it's also the direction of greatest increase, but in this case, when we're thinking of this as a level set, what is the relationship between the gradient at a point and the level set there? So the gradient is also from that section 2.6. Geometrically, what relationship does the gradient have with the level set? The gradient is blank to the level set. Yeah, good. Someone in the chat says normal. It's normal to the level sets. Okay. In this case, we had a nice formula for that. I'm going to go back to it. You had this. Now, it's not immediately obvious why this is normal to this, but basically what that means is we get boom, 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 something like this, like a gradient field that looks like this. Okay. And remember, we're trying to find the point where this blue graph is biggest along this circle, right? So if I'm going to zoom in a little bit. I'm going to zoom in on this graph a little bit because I think that's going to be helpful. Just make it a little bigger. So what's happening is the orange arrows are going up and to the right, right? And the green arrows are going around in a circle. The orange arrows are telling us the greatest increase for the function f, right? And the green arrows are telling us just kind of, this way is normal. This is normal to this vector here, to this set here. So if we think about where this function is going to be biggest, it's going to be up and to the right, up in this direction. Where it's going to be smallest is up and to the left. If we were to zoom in right here, zoom into this point right here. Let me actually draw some stuff here. If we were to zoom in right here, we'd get a slightly different picture that looks like this. So we'd have the gray part of the circle, and then we'd have these green arrows kind of going right normal to this. Okay. And then at one of these points somewhere, you'd have that this orange arrow lines up perfectly with the green arrow. Over here, it's going to be slightly too not steep enough, and over here, it's going to be slightly too steep, right? So over here, these two, they don't line up, but at this one, they do line up, right? And what does it mean when vectors line up? If vectors line up, are pointed in the same direction, but they're different sizes, then this delta G, or sorry, nabla G, the gradient of G, is just a scalar multiple of the gradient of F. The gradient of F. and the gradient of G, they're related by just some scalar multiple. That scalar multiple is just the amount of stretch it needs to get this green to this orange in length. Okay. And so, right over, that's us realizing that this orange is telling us where do we go to get as big as possible. And so over here, it's going to be right, like the arrows I had before, they're not quite in line with the orange arrows. And so these green arrows are not quite in line with the orange arrows, which means that there's still a possibility to get bigger, right? Because if the orange arrow is pointing like this, not quite in line, then that means if we move slightly to the right, we can get something bigger. If the orange arrow is not quite in line with this one, that means if we move slightly this way, we can get closer to the arrow, okay, or to the biggest point. So at this point, it's kind of happening. Now, at this point over here, if I were to zoom in, let's say somewhere over here, then we'd have something kind of the opposite happening. So we'd have the circle, kind of the other side of the circle, and we'd kind of have these green arrows kind of pointing out. Okay. And now this this orange arrow, which is moving up and to the right, right? Over here, these are kind of at a weird angle. Over here, these are at a weird angle in the other direction. Maybe I'll make that a little more dramatic. Maybe I'll do, oops. Yeah, maybe I'll do this. Right, so this is not a perfect, but somewhere here in the middle, I think actually this is a more accurate point here. We're gonna get that these are exactly in the opposite direction. This is the same picture as this. This is the same equation, I should say, as this, except that lambda in this case would be a negative number. Okay. Does that make some sense? So this is kind of the picture I have in my mind for remembering why the Lagrange multipliers work, right? This is telling us where do we go to get f as big as possible, okay, at a given point. And G is telling us, okay, this is my normal direction. This is normal to the constraint. If those aren't lining up, for example, if this is the direction of greatest increase and this is the normal vector, then that means if I move this way along my level set, if I just move this way a little bit according to this vector, then I can get a little bigger, and I just keep getting bigger, and then once they're lined up, there's nowhere bigger I can get along the level set. I kind of like to think that these orange or these gold, whatever color you want to say, are kind of pulling on the green arrows, telling it where to go. So like over here, it can pull it a lot because green is kind of pointed in the other direction, and then it keeps pulling until it lines up, and then there's nowhere bigger it could possibly get. Does that make some sense? Okay. Any questions on this slide? We can jump into some more examples here. Okay. Cool. So let's jump into another example here. If you have questions, feel free to slow me down. So now we're going to find the extrema of this function here with the subject to a certain constraints here. So in this case, notice that the constraint is a little bit different. So actually a couple things I want to point out. First of all, this phrasing subject to is a common way for them to say that this just means they're telling you what this is the constraint right here. It's the language they use. Now notice a couple of slides ago, and on this example, we had an equal sign, and I even pointed it out. But here we have a less than or equal to. So that means that our region has an inside and a boundary. Remember, the method of Lagrange multipliers only works on the boundary. And so if you want to find stuff inside of it, so if you want to find stuff on the inside, we have to find critical points the old-fashioned way. I say that old-fashioned as in 2 sections ago, or I think even last section, where you use the first derivative test. So for critical points on the inside, we use first derivative test. So first derivative test on f. So we take the gradient of f, or technically we say df, and we find the critical points. So set this, take the derivatives of this guy, so we get x squared plus 2xy, and then in the y entry we get y squared plus 2yz, and then in the z entry we get y squared plus z squared. Okay. So then we set each of these equal to 0 and we see if we get anything interesting. In this case, for sure, the first critical point we're going to get is, can anyone see it? Like there's one way to make these, right, this 0, 0, 0. There's one way to do that relatively easily. And I think that's the only way, in fact, in this case. I can say x equals 0, y equals 0, and z equals 0. If all three are 0, then that's enough here. Then that gives us 0, 0, 0. And I think that's the only critical point in this case. You could let's see if there's anything any other trickery happening here. So this one can't be 0 because these are both positive. These are both positive numbers. So it can only be 0 if x, y, and z are 0. So then that tells us that y and z have to be 0. And then that, yeah. So basically, let me spell out what I'm saying. X squared plus 2xy equals 0. X squared plus 2yz equals 0. Y squared plus z squared equals 0. So y squared plus z squared equals 0 tells us that y squared has to equal z squared, or y has to equal z has to equal 0, right? Because no matter what else we plug in to y and z, if we plug in anything that's not 0 for either of these, then we're going to get something positive here, okay? Because even if you plug in a negative number and square it, you get a positive number. So you can't ever, these will never cancel out to give you 0, these terms, unless both of them are already 0. That should be a z. Okay. So y equals z equals 0. So then we combine that with these two, and we get x squared plus, I guess either of them, you don't have to do both, 2 times x times 0 equals 0, which then means x squared equals 0, which then means x has to equal 0 as well. Okay. So this is going to be, this was not just, it wasn't just a, I mean, I found it as a guess and check, but then this verifies that this is the only critical point, because there's no way, there's no other solutions to this guy. And then as soon as we get this one, this solution, that gives us the solution for x. There's only one option for x as well. Okay, cool. Any questions on that? So that gives us our first, so if we're keeping a list of candidates, we get 0, 0, 0. Now, technically, I should be making sure that it satisfies this constraint. In this case, it does, right? So it's 0, 0, 0 definitely satisfies this constraint. It's on the inside of this, because this is, right, this is going to be 0 squared plus 0 squared plus 0 squared. So we get 0 is less than or equal to 1. That's totally okay. So now we want to check. So this was on the interior. Now we want to check the boundary. So on the boundary, we're going to use Lagrange multipliers. So we're going to set this function over here. This is going to be equal to, this is going to be g of xy. Okay. XYZ, I should say. Okay. And that on the boundary, we're looking at g of xyz equals 1. So you could think that the less than part of this is telling us like we're on the inside of this shape, right? That's what this is telling us. That's what this first derivative test takes care of, the inside stuff. And then this equal to part is telling us there's a boundary included in that. And that's what the equal to, that's what the Lagrange multipliers is going to do. Okay. And I'm going to outline this a little more precisely on the next slide. I'm going to kind of give a step-by-step of everything. So let's go ahead and do this, use this method of Lagrange multipliers and see what we can get out of this. Okay. So let's start by taking the gradient of G. Okay. This is going to be 4x, 2y, 6z. Okay. And now the method of Lagrange multiplier says that we set this gradient, right? So if we think of this instead of as a matrix, as we think of it as a vector, that's just the gradient right here. We set this equal to this times some lambda. And so now I'm going to set that up. In this case, the first coordinate would give us x squared plus 2xy equals 4 lambda x. And then the second coordinate, x squared plus 2yz equals 4 lambda y. Okay. And then the last thing here is x or y squared plus z squared, 6z squared, plus z squared equals 6z. But then we also have to include the constraint here. So 2x squared plus y squared plus 3z squared equals 1. Okay. I missed a lambda here in this one. So there should be a lambda on these three. Okay. Now it's a matter of solving these, which I think is going to be easier said than done. Another typo there. It should be a 2. So let's see. So let's see. Did I work this one out ahead of time? I don't think I did on this one. Okay. Yeah, so definitely the hardest part of these problems is going to be this step here where you're solving for the candidates using the Lagrange multipliers. As we saw in this first example I did, that was not, this was a relatively easy one, and even this one took several steps. This one looks like it's going to be even a little more involved. I'm going to need a little more space, so make another page there. I think what I want to focus on is this first equation right here. So what I'm going to do is move everything to one side. So I get x squared plus x times 2y minus 4 lambda. And this is going to equal 0. So I moved this term over and then factored out an x from that first term there. Okay. And then they can factor this again to get x times x plus 2y minus 4 lambda equals 0. So then there are two parts of this solution. So you get an x equals 0, and then an x equals 4 lambda minus 2y. Right? Basically, you have x times x plus this, and that's equal to 0. So your two solutions are x equals 0, and then this equals 0, which I then just moved everything over and got this here. Okay. So let's see how many solutions we're going to get. So maybe I can use, if I follow on this x equals 0 path, right? I'm going to eventually have to come back to this one here. But for now, I'll follow this x equals 0 path. And if I follow this x equals 0 path, then I get, from this equation, I get y squared plus 3z squared equals 1, right? So again, that's following this path. It's going to be hard to stay organized with all of this work, but I'll try my best. Actually, I'm going to start this on another page. So again, this is the x equals 0 path. I took this bottom equation, and that gave me y squared plus 3z squared equals equals 1. And then I'm looking at the equation right above it, which is y squared plus z squared equals 6 lambda z. Okay. Now, if I subtract these equations, then I get 2z squared equals 1 minus 6 lambda z. Oh man, maybe this was, I should have done this one in advance so that I could foresee all of this. Let's see, what else can I do? It does take some cleverness sometimes. Let's see. Let's see. Yeah, so this, I think, ended up being more involved than I was planning on for this problem. Let's see, is there some kind of obvious solution to this? Don't think there is. So we don't get anything obvious like all zeros, because all zeros wouldn't satisfy this last one. It wouldn't live on the boundary. Let's see. Yeah, I think I don't want to waste more time on this example because I should have, this is what I get for trying to make up an example. So this constraint actually ended up being more difficult than I planned. So this system of equations is actually not the easiest thing to solve, if you haven't noticed already. So I think for the sake of time, I'll skip this problem just as a, just to clarify. I made this problem up. It's not like I pulled it off of the homework and I'm not, and it's something that you have to do, but I can't do. So it's difficult because I made it up and didn't work it out ahead of time, not because this is like an actual problem I would expect of you. So the ones from the homework are should be more manageable. Maybe because of this, since I'm not going to finish this one, maybe I'll go back and do one of the ones from the homework to save you some time. But the principles are still here, right? We started by, when we saw the less than or equal to, we did the first derivative test, and then we tried to use the method of Lagrange multipliers. It just got too difficult. Not impossible. I think there is a way to do it. I think I would need to work on it for a little bit. I should have worked on it before showing it to you all. And so the method of Lagrange multipliers, like I said, is probably going to be the most difficult part. So let's kind of summarize that strategy that I said. So constraints that look like this versus constraints that look like this. So this is just to highlight here, geometrically, there's just the boundary. The boundary. And over here, this is interior plus boundary, and boundary, I should say. So over here, maybe it would look something like that. Whereas over here, you can have the same shape, but it includes the stuff on the inside. Okay. So the steps here, they're very similar to the steps in the last chapter, in the sense that your first step is to find the candidates in both of these candidates. But the how you do that is going to be different for each of these. In this case, you're going to just jump straight to the method of Lagrange multipliers. That means that you set up this equation and solve, which is easier said than done, right? We just saw that. Over here, you're gonna, for this one, it's gonna be a little different. You're gonna use the first derivative test on the interior, and then you're going to use the method of Lagrange multipliers for the boundary. Okay. So if it's just the boundary, if there's an equal to sign, you're just using the method of Lagrange multipliers. If you have an interior, then you can use the first derivative test on the interior and then the method of Lagrange multipliers on the boundary. And then regardless of which of these you do, you're always going to go to step 2, which is plug in the candidates. The biggest, remember, ultimately both of these methods are for finding extrema, and so we're going to look at for the biggest and the smallest when you plug in these candidates, and that's going to give you your minimum and your maximum and your minimum, respectively. Okay, cool. Any questions on this outline? My handwriting isn't great, so let me know if you need me to clarify any of these steps. But you're going to set up this. So like I said, the hardest part of this, the first derivative test is relatively easy, right? You take a gradient and then you set it equal to 0, which tends to make easier equations than the Lagrange multipliers. this tends to make the equations pretty difficult because there's stuff on the left and on the right. Like we just saw, if I just try to make up a problem, the equation I get is not going to be something that's super easy to solve. So like I promised, I'm going to do an example from the homework. I have it pulled up here. So again, this is the general strategy, but I want you to see a fully worked out example without me fumbling it. So I'll pick one from the homework. So we have right, so find, so let me find the extrema of f of x, y, z equals 2xyz on the unit ball x squared plus y squared plus z squared is less than or equal to 1. So notice here, this is, the constraint is much simpler in this case. I thought I would make things more interesting by adding coefficients, and that ultimately doomed me. Also, the equation itself is a little simpler in this case. Okay, cool. So I'm not saying this is necessarily going to be an easy problem, but it should be much more doable. So let's start again. We have a less than or equal to, so we go to our chart here and says, okay, we got to find candidates, of course, but how do we do that? Well, in this case, we're going to start with the first derivative test on the interior. So we're going to compute the gradient of f. In this case, that's going to be 2yz, 2xz, and 2xy. And of course, if we set all of these equal to 0, 2yz equals 0, 2xz equals 0, and 2xy equals 0, right? So again, the sort of guess and check solution is that you get a critical point at 0, 0, 0, right? So definitely that satisfies this. So definitely you get a 0 at 0, 0, 0, you get something. But how do you know you don't get anything anywhere else? Well, if any of these, let's imagine a universe where we try to say x is not equal to 0, but then y has to be equal to 0, and z has to be equal to 0. And so actually that might be allowed. Let's see. Is that the case? Yeah, so I guess you can have, you just need any two of them to be non-zero. But I think because of that, yeah, something weird happens when you let other things not equal 0. But I think for the sake of this problem, we can focus on just this one solution to this here, and we'll write that as our list of candidates there. Start that list here. Basically what's happening is this function is, it's doing weird stuff if you just go in any fixed direction. If you go along the x-axis, y-axis, or z-axis, basically, you're going to get some kind of something weird happening. But because of this, it's not changing in any of those directions. And so you get the same behavior at this, or the origin is going to tell you everything. So well, yeah. So I think if you see this sort of thing on like a quiz or something, this would be fair to take this as the list of candidates right here. Okay. Or for at least for the first derivative test. But now we need to use Lagrange multipliers on the boundary. So in this case, we get we're going to do the gradient of g. So for example, this here is g, and we get 2x, 2y, and 2z. Okay, and this is the fun part. So we get four equations. So we get 2yz equals lambda x, 2 lambda x, and then we get 2xz equals 2 lambda y, and we get 2xy equals 2 lambda z. And then, of course, we get x squared plus y squared plus z squared equals 1. Okay, cool. So first thing we can do is we can say, we can divide everything by 2, get rid of all of these 2's on this. And so we just get yz equals lambda x, xz equals lambda y, and xy equals lambda z. Okay. And then what I'm going to do is I'm going to isolate all of it. So I'm noticing is that these are basically isolated here. The variables themselves are basically like isolated. So we can just move the lambdas over. So again, these three are kind of turning into this by dividing by 2. Now divide by lambda. I could have divided by 2 lambda all in one swoop and gotten this, but I get x is equal to yz over lambda. Y is equal to xz over lambda. And z is equal to xy over lambda. Okay. So let's see what I want to do next. So let's start by, there's a lot of symmetry if you can tell, right? Like if you, the 3 variables have basically the same role. But so it's gonna feel a little repetitious what we're gonna do next, I think. But what we can do here, one option is you can take all of this and plug it in your x, y, and z and plug it in here. And we might eventually do that, but I think right off the bat, that's not going to give us enough new information. And so what I'm going to do is I'm going to take, for example, this, I have solved for z here. I could then plug this in up here for z. Okay, so I can even go down here if I want to. Do I want to do that? Actually, I think I'll plug this in here, and that gives me y is equal to x times xy over lambda squared, right? So there was a lambda here already, and then when I plugged this in, there was another lambda there. Okay. So now what I'm going to do is I'm going to move this lambda over. So I get lambda squared. And then I can divide by y on both sides, and I just get x squared equals lambda squared. Oh, okay. That's also I think I like that a little more. I think what you're saying is a little more clever. I think I was gonna land on that here anyway. So you could keep taking this path, but I like what you're saying there in the chat, which is you just take these three equations, and so this is an option. And if you keep going, you'll get the same thing as what I'm about to do, but you can multiply this one by x, this one by y, and this one by z. And so you get x squared equals xyz over lambda, and then you get y squared equals xyz over lambda, and z squared equals xyz over lambda, right? So multiply the first equation by x, second equation by y, and the third equation by z, and you get exactly this, which this is one of these cases, and I'm glad you brought this up, because this is one of these cases where we can see that it turns out that we're not going to actually end up having to solve for lambda, because what this is telling us is, yeah, it's telling us that each of these is equal to this value, but it's telling us that they're all equal to the same value. So x squared plus y squared plus z squared equals, or I guess x squared equals y squared equals z squared. And that's equal to this stuff, but we don't actually care that much. Okay, x squared equals y squared equals z squared. If we make that substitution over here, right, then we get x squared plus y squared plus z squared equals 1. Okay, or sorry, I'll say x squared, 3x squared equals 1, right? If we just substitute y squared for x squared and z squared for x squared, right, we plug both of those in here, then we get this, and we get that x is equal to plus or minus the square root of 1/3. You can rationalize that denominator if you want, but I won't. The square root of 1/3. And you could have done this with x, y, or z. So basically, we get, let me give myself some room. So let me repeat what I said. So x squared equals y squared equals z squared. Make that substitution into this equation. We get 3x squared equals 1. Okay. And then we get x equals plus or minus the square root of 1/3. Again, you can rationalize this denominator or you cannot. But then y and z can also equal plus or minus 1/3. Actually, I want to write it this way, because just because the three numbers square to the same number doesn't mean that they're the same. Meaning, right, each of these numbers, x, y, and z, can be plus or minus this number, plus or minus the square root of 1/3. But they don't have to all be plus or all be minus. They can be different signs, because when you square them, they'll all be the same. They'll all equal 1/3. Okay, and so there's a bunch of candidates here. We get the square root of 1/3, square root of 1/3, square root of 1/3. Okay, and then basically we can just make any combination of these negative. So we could say negative square root of 1/3, and then the rest are still positive. How many of these will we have? Can anyone count that in their head? So yeah, the square root of 1/3. I know the answer. It's just if you count this 0, 0, 0, it's 9 total, but should be 8 with just the on the boundary here. Okay, but yeah, that's the right idea. So square root of 1/3, square root of 1/3. So far I've just done the one that's all positive, then the one that has these three negatives, or yeah, sorry, just one negative, and then you have two negatives, and then you have just all three negatives. Yeah, 2 to the third plus 1. That this plus 1 is coming specifically from this extra 0 here, this extra candidate here. So we get square root of, now we have any two being negative. Okay. And then negative, so yeah, it's gonna take me a while to write them all down. There you go. And then just a note, as I was moving over here, you see I got x squared equals lambda squared. Basically, my next trick was just going to be to do every combination, and you get x squared equals lambda squared, y squared equals lambda squared, and z squared equals lambda squared. And so they all equal lambda squared. And so you then after that, it just follows the same thing here. Square root of 1/3, negative square root of 1/3, and 1/3, negative square root of 1/3. So that's all the ones with 2, and then we just have all negatives. Okay. Cool. So we're trying to find the extrema of this function here. So technically, we have to plug in all 9 of these into this equation over here. But we're going to notice after a couple that there's a bit of a pattern. Okay. Now, on the problem itself on the homework, it says find the maximum and minimum values. So we don't actually care about the inputs. We just care about what's the biggest output we can get and what's the smallest output we can get. So if we go down to, I just make myself an extra page here. And if I was going to actually test these candidates, I would say let's start with just f of 0, 0, 0. And of course, that's 0 times 0 times 0, or 2 times 0 times 0 times 0. So we just get a 0 there. Okay. So now let's try f of 1/3, 1/3, 1/3. The square root of 1/3. Square root of 1/3. Square root of 1/3. This is going to be 1/3 to the 3/2, because basically I'm just multiplying these 3 numbers together, right? Oh, times 2. 2 times that. So 2 times 1/3 to the 3/2, right? So I just cube 1/3 to the 1/2, and it gives me 1/3 to the 3/2. You can also say the square root of 1/27. There's a lot of ways to interpret this to simplify this arithmetic. But basically, you get some positive numbers, so we definitely got something bigger than this, right? The important part of this step is not how good is your arithmetic, it's how good are you at looking at a number and comparing it size-wise to another number if you're not just given some decimal expansion, right? I don't want to have to go get my calculator out, plug this into a calculator. I just want to say, this is a positive number, so it's bigger than this. Now, the cool thing is that if I make any one of these negative, I get the same thing. Right? So it doesn't matter which one I make negative. Okay. So just this one, if I just make this one negative, that's the same as, so this one, let's see, maybe I'll use purple. Purple is going to represent this one, and this one are all going to have the same output. It's going to be this one here, and that is the same value, but with a negative sign, right? Because you have negative times positive, so I get -2 1/3 to the 3/2. Okay. And it turns out that these are the only 2 possible outputs because we're multiplying the same number 3 times, except it's just a different number of minus signs. So we have no minus signs. We have 1 minus sign here, here, and here. We have 2 minus signs here, here, and here, and then 3 minus signs here. So the purple stars are all going to be negative, and the green stars are all going to be positive. Okay. Now, since the problem was originally, I don't know if I didn't write it here, but on the homework, it's asking for the maximum values and the minimum values. And remember, when you see value, it's just the output. It's 2 and 1/3 to the 3/2, and then the minimum value is -2 times 1/3 to the 3/2. Again, I'm just looking, I'm not like computing these with a calculator to know anything. I'm just saying, okay, we have 0, a positive number, and a negative number. The biggest one on that list is the positive number. The smallest one is the negative number. Okay. So you just have to be able to compare the two numbers. You don't have to necessarily know exactly their decimal expansion. Okay, cool. Okay, so that was this problem. I think it shows this outline pretty well. It also shows that even in a problem like this, the Lagrange multiplier step was still not super easy. It was just doable as opposed to the other one I tried to do before. Okay. And you do have to get creative, like this step over here, going from here to here, like that's not necessarily obvious to everyone. This step I think was maybe a little more clear because once you have z equals something, you want to say like, okay, I can substitute z for anything in these other equations. And that's a pretty common way of proceeding. Once you have z equals or x equals or something like that, do some substitution. And then you can kind of do that. So it does take some creativity, and there's multiple different ways to do it, but you can land on an answer regardless of how you do it. Okay, cool. Any questions on this problem? Okay. I have one last example from this section, and then we can we'll probably call it a day. I thought we were going to be able to start the next chapter, but it looks like because I flubbed a little bit, we'll be right on schedule as opposed to ahead of schedule. So here is the last example I want to do. It's similar to a problem that comes up on the homework. So this one, it's kind of interesting because at first it just seems kind of like, okay, like a random like riddle or something. What is the smallest that the sum of 3 positive numbers can be if their product is 8? Okay. If their product is 8. So basically what this is doing, what we can do is we can set this up as one of these extreme value questions. So what this is, with the sum, right, we have the sum of 3 positive numbers. That's just saying, we'll just give them a name. So x, y, and z are your 3 positive numbers. Okay. And the positive part here is just a little technicality. I'll brush upon it when I get to the relevant step. But for now, we can just say, okay, this is just a function where we add 3 numbers together. And we're trying to find a minimum for this function, right? Because we're trying to find a minimum for this function right here. What's the smallest this can possibly be? Okay. But we have a certain restriction. We know that their product is 8. So what does that mean? That means that x times y times z is equal to 8, which means that if we can just label this our constraint function. So we have a constraint, we have a function that we're trying to find the minimum value of, and that means that we can just use our method of Lagrange multipliers. Now, one thing I want to note right off the bat is that this function can't have a maximum if you're looking at positive numbers, right? Because even if I restrict the product to be 8, I can make x as big as I want, and then make y just 1 over x, and then z can be equal to 8 or something like that. Or I can choose these 3 numbers which satisfy this equation that make this sum super huge, right? No matter how big right, like because I'm working with real numbers and not just like natural numbers, I can make these numbers huge, and that means I can make their sum really, really big, as big as I want it to be. So this function has no maximum, even if I restrict to this being here. So like I can make x equal 1 million, y equal 1 over 1 million, and z equal 8, and then that satisfies this, but the sum is over 1 million, right? And I can do the same thing with 10 billion, however big I want. So this sum can get as big as I want, but the question is, how small can I make it, right? Definitely, right? It's going to be a positive number if I'm adding 3 positive numbers together. So it's not going to be, it's definitely not going to be smaller than 0, but maybe it's, I can't plug in all zeros because that doesn't satisfy this constraint. So now we can use the method of Lagrange multipliers to actually figure this out. Now, because I have an equal to, I don't have to worry about the first derivative test. I could just jump straight into the Lagrange multiplier stuff. So let me compute the gradient of f, which is nice in this case. It's just 1, 1, 1. And the gradient of g, which is equal to something similar to the problem we just saw. We have, let's see, yz, xz, and xy. Okay, this one I did ahead, so I believe I did. Yes, just to make sure that it was reasonably doable. So you get, so we can set this up just like we did before. So we get 1 is equal to lambda yz, 1 is equal to lambda xy, and 1 is equal to lambda x y. No, sorry, I messed one up. Xz should have been there. Okay, there you go. So 1 is equal to lambda yz, 1 is equal to lambda xz, and then 1 is equal to lambda xy. And that's what we get by setting this just 1, 1, 1 equal to lambda times these 3 here. Okay, and now we can start to see a similar trick to the trick we used on this last problem, right? When we were at this step, we realized that we can make the right-hand side the same by just multiplying by something on each of them. We could see that here too, right? On this first one, if I multiply by x, I get that x is equal to lambda xyz. The second one, I can multiply by y, and I get that y is equal to lambda xyz. And on the last one, I multiply by z, and I get lambda is equal to z is equal to lambda xyz. And so the point of all of this is that I get that x equals y equals z. Okay. And so I can remember I have a third equation here, which is that xyz is equal to 8. Okay. Okay. Now I can plug this in over here. I get x cubed equals 8, right? So x has to equal positive 2, right? Remember the cubed root, you don't get a plus or minus, right? You just get a positive, right? So that means that x, y, z is equal to x equals y equals z is equal to 2. And so then the only candidate we have is 2, 2, 2. Now, depending on how I took this one from the homework, but I think I rephrased it from how it was in the homework. On the homework, it said find 3 positive numbers, which such that their sum is minimal and their product is 8 or something like that. I'm saying what is the smallest the sum can possibly be? So that's slightly different. This is asking, it's not using the same phrase, but it's asking what's the minimum value of this function? So what's the smallest the sum can actually be? Well, these are the 3 positive numbers that give me the smallest sum. So the sum itself is 2 plus 2 plus 2. So we get 6 here. So if you have 3 numbers and their product is 8, the smallest their sum can possibly be is 6. Okay. Cool. Any questions on that? If the question was asking for largest, then in this case, we don't actually have a solution. Because like I mentioned at the beginning, I can make the sum as big as I want it to be. There is no maximum. This function doesn't have a maximum. So I'll even write that here. This has no max with this constraint. So you might think like, that's weird. Every problem we've done so far has had a minimum and a maximum, right? In this case, there's no maximum because this is not bounded. So if you remember back to the theorem I said at the end of the last section, your constraint has to give you something closed and bounded. Since this is not bounded, I can make X, Y, and Z as big as I want them to be. Then I can make this sum as big as I want it to be. Okay. Cool. Now, technically, I'm missing, I never used the fact that they were positive, but I used it implicitly. So what I could have said is what if I just let any two of these be something negative, right? Then that still satisfies, like I can still make, for example, I can make -2, 2, and 2. Sorry, if I make -2, -2, and 2, then that still satisfies this constraint, and it makes this some negative number. It makes this -2. And so I can make it smaller if I allow for negative numbers. But if I'm just allowing for positive numbers, then this is going to be as small as I can make it. Okay.